Hello, everyone. It is my pleasure to welcome you all to another WASH Canada talk. Today we have Dr. Sara Beck, who is an assistant professor at the University of British Columbia. Her background is in environmental engineering, and her research uses microbiology and molecular biology tools to improve water treatment and water reuse processes. Today, she will be presenting about her work on decentralized UV disinfection systems in low resource contexts. Sara, thank you for joining us today. Over to you.
Okay, thanks very much for having me. I will go ahead and share my screen. How's that?
That's good, Sara.
Okay. Okay, great. Yeah, thanks everyone for having me. It's good to be a part of these WASH Canada talks. In fact, I'm honored to be on the CREATE grant, the NSERC CREATE grant, as one of the co-investigators. So that's the grant that's supporting all the WASH Canada talks, and I'm honored to be a collaborator with that. So today I'll be talking about decentralized ultraviolet disinfection systems in low resource contexts, and actually just presented this at the International Ultraviolet Association conference, the World Congress in Dubai recently. So this is a similar talk. And it's great to see everyone in the audience. I recognize a lot of members, a lot of colleagues and collaborators, and also members of my research team and some of my classmates too. So great to see everyone. So first, Alexa gave a brief introduction, but first an introduction to my research group. So I lead the Beck Research Lab at the University of British Columbia. There's our website at the top, Beck Lab UBC, if you want to learn more about what we do. But basically our goal is to understand and prevent pathogen transmission at the confluence of public health, water quality, and innovative water treatment solutions. So we focus a lot on decentralized treatment systems, primarily water disinfection, but also surface disinfection, and then also some wastewater reuse systems as well. So check out our website and learn more about our team there. So I wanted to mention that this basically my talk will be covering a group of 19 case studies that we all put together where ultraviolet light was used for decentralized water treatment systems. And this initiative came out of the UN SDG task force from the International Ultraviolet Association. So basically we have the International UV Association, which is a network of experts in the ultraviolet disinfection industry. And we put together a task force for looking at how do we address the United Nations Sustainable Development Goals, primarily goal number 6. So how do we address UN SDG 6 for clean water and sanitation for all? And so this initiative came out of this task force effort. So the work I'll be talking about was all put together by this case study group. This is a case study working group. We actually have a publication, and the lead author on the study, who I saw is on the call, that's Nathan Moore. He and Ron Hoffman are from the University of Toronto. We also have Dana Pausti, Asaf Pras, and Hadas Maman from Tel Aviv University. So the top row, along with Rachel Gare from Purdue University, we had a working group to discuss these case studies and put them all together. And then we solicited the help of Carly Wong, also from University of Toronto, Daniel Ma from The Ohio State, and Carl Linden from the University of Colorado Boulder. So this initiative is part of a broader effort. So I wanted to acknowledge all of the other co-authors from the manuscript. But basically, this is covering a case study, so 19 different case studies to highlight the wide range of ultraviolet disinfection systems being implemented for decentralized water treatment in low and middle income or humanitarian and rural settings around the world. And actually, if you're interested, there's a preprint version online. So I show the title of that if you want to look for it. It has not yet been published, so we're actually making some changes mainly to the conclusion and resubmitting it for publication. But basically the goal of this case study compilation is we want this to be the initial knowledge base, like the initial repository for information about where UV systems have been used in low resource situations. So that can cover a broad scope. And I also want to mention that when I'm talking about ultraviolet light in this context, this is human-made UV light or UV light from human-made sources. I'm not covering solar disinfection. So solar disinfection, while that also uses ultraviolet light from the UVA and B ranges, I'll be talking about UVC, which is also produced by the sun, but it's absorbed by the Earth's atmosphere. So, so we're using UVC from low pressure mercury lamps and also light emitting diodes, but these human-made devices. So just wanted to make that distinction. So this compilation, it's 19 case studies, and it covers a range of regions. So it spans across 4 continents, Asia, Africa, there's one in Europe, and then North America. And it's a wide range of environments. So we talk about instances where UV disinfection was used to treat drinking water for schools and hospitals, smaller communities, households, and healthcare facilities. And then also what's unique is that we cover a wide range of water sources. So we cover groundwater from wells, surface water from springs or rainwater collection ponds, cover rainwater harvested from a roof. Also, there's a case study that involved trucked water and then piped water. And then there's one involving wastewater as well. So we try to cover a broad range of water sources and then a broad range of energy sources as well. So a majority of the studies use grid or solar power, and there's one on battery power as well. And then for UV systems, we're using the low pressure mercury lamps or ultraviolet LEDs. And these are systems that operate at flow rates between 0.5 to 50 liters per minute. So this, I'll be going over them in more detail, of course, but I wanted to first acknowledge all of the authors of each case study that we then compiled into this broader document, and just mention that, okay, we have one in Canada from a First Nation in Canada, one from the Dominican Republic, 3 from India, 1 from Laos, People's Democratic Republic, 2 from Kenya, 1 from Mexico, 1 from Nicaragua, 1 from the Philippines, 3 from Rwanda, 1 from South Africa, 1 from Tanzania, 1 from Uganda, 1 from, it can be operated either in Ukraine or in the USA. It was for emergency water treatment, and then another one from the USA. So here's a list of all of the individual authors who submitted case studies, and I wanted to thank them for helping us out with this. I also wanted to mention that along with the case study manuscript, we have an interactive map of the case studies, and this is on the IUVA, that International Ultraviolet Association website. And you see the link at the bottom, iuva.org. But basically the map is so that you can go and click on any one of these pins and learn more about the system in place and learn about what kind of system did they use, what kind of challenges did they encounter, how did they work around those challenges, how did they troubleshoot. And so this is really to serve as, like I said, a knowledge base. And we want people to, if you're a practitioner who's considering using ultraviolet light in a certain situation. In fact, I was recently contacted by someone at Cox's Bazar refugee camp in Myanmar asking about using UV LEDs for treating wastewater there. And so we want this to be a growing database where if people are using UV, they can add information about their system here, and then other users or other practitioners can learn. And we also want it to be searchable so that you can search by low pressure, search by LED, or search by school or hospital or community or intermittent water or solar power. So we're working to add that capability. But please check this out. And if you have a case study, we're opening it up for adding that to these to this website, so we can give you more information about that. Okay, so I'm going to start off by giving a broad overview of all of them, so all 19, and then at the end I cover about 4 of them in more detail and talk about some of the highlights. So starting off with North and Central America, so I'll start from the top left, and then I'll go clockwise around the screen. So the very first one, this was in Lytton, which is a First Nation in British Columbia here in Canada. And this was done in partnership with the Rezo Center for Mobilizing Innovation. This was done through Majid Mohseni, who's also a professor here at UBC, and through a collaboration with the Lytton First Nation. And it was to serve 5 households. So they started with surface water from a creek and ran it through a series of 3 different filters, and then disinfected it with low pressure ultraviolet light. And one of the challenges encountered was turbidity and fluctuations, since it was a surface water sources, fluctuations with turbidity from the annual snow melt. So next up, we'll go to the one in the top right. This was in Kentucky, and this was the one that was also operated in Ukraine. And what they developed here, it's called the WOW cart, or the Water on Wheels cart. This was done through the U.S. Environmental Protection Agency in collaboration with WaterStep, which is a non-governmental organization in Kentucky. But this was created as a mobile water treatment system. And I actually got to see it. I got to see it when I visited the US EPA for a conference last year. So they used ultraviolet LEDs. Actually, they have a multi-barrier treatment train. Those in my class hear me stress about the importance of multi-barrier treatment. So this was filtration, and then also activated carbon, ultraviolet LEDs, and then chlorination. So that's the one that was up here for Kentucky. The next one, this was in La Vega, which is in the Dominican Republic. This was a collaboration between, well, it's Purdue University. So this one was submitted by Chip Blatchley and Rachel Gare. And here they were operating at primary schools in the DR. And here again, they also had sand filtration, cartridge filters, and then UV and chlorine. And one of the things that I wanted to point out with this study, since it was done at primary schools, they had the challenge of what happens when school is no longer in session, and is the system still maintained when you have that intermittent water, or when you have intermittent operation and maintenance. So that's a challenge that we found that came up with some of the systems that were installed in schools. The next one in the lower right, this Rama K Island in Nicaragua. This was done through Messiah University and submitted by Daniel Ma, a PhD student at Ohio State. And they also had a multi-barrier treatment train. So you can see well water into a pressurized tank going through reverse osmosis, and then UV. I believe this was low power or low pressure UV that was used as a disinfection step. And then that treated water was stored in a water storage tank. The next one on the bottom middle. So this is, these are case studies for communities in Mexico. So this was in Baja California Sur and Chiapas, Mexico. And this was done through a non-governmental organization there called Cántaro Azul. And this was submitted by Dr. Fermin Regadas. And there are 2 different iterations for this one. In fact, I'll talk about it more. But yeah, I'll actually wait to talk about this one because it's one of the 4 that I highlight. And then the lower left corner, so this is Jamestown, Colorado, which is a small community outside of Boulder, Colorado in the United States. And this case study was submitted by University of Colorado from Carl Linden and Natalie Hull. And here they have a small community, and they're already using chlorine for disinfection. And so they tested out an ultraviolet LED system and had it running in parallel with the chlorine. So basically 2 trains operating in parallel to see how the LED system worked over the course of 1 year. It was a 1-year study, and that one has been published. So there's more information about it online. Now I'll go to the studies from Africa. So we had 8 different studies for the continent of Africa, and I'm going to start again in the top right, and I'm going to go around clockwise. So the first one in the top right, this is in Kisii, Kenya, and this is one that we're working on with UBC in a community called Nyame Socho. And this is a community of the postdoctoral fellow in my group, Dr. Paul Nkundi Nyangaresi. So this is for treating water at the household level, and I'll cover that one in more detail. One of the things that I wanted to mention about that one is that it's gravity driven. So rainwater treatment system, but gravity driven. A lot of the other studies, not all of them, but a lot of them have pumps. And so we're trying to reduce costs by eliminating the need for a pump. The next one is Eldoret, Kenya. So this was one that was also submitted. This is Purdue University from Chip Blatchley and Margaret Bousset. And here they were working at a primary school serving 400 people. The one mentioned in the lower right, this is in Tanzania, and this was submitted by the University of Toronto, Carly Wong and Ron Hoffman, and they were working in collaboration with WaterAid Tanzania. But here, these systems were operated at 6 different healthcare facilities around Tanzania. And you can see in the schematic, they had an elevated tank. Where's my cursor? Elevated tank going through a UV device. Basically, they were collecting water from rainwater and running it through a first flush or a washout chamber, and then storing the treated water in an underground tank prior to use. In South Africa, I also talk about this one in more detail. This was one of the UV waterworks. You'll hear me mention that a couple times because it was used first in India, and then the second iteration was done for an orphanage in South Africa. And so here, one of the things that's unique about this is that they had the UV lamp above the water, and that was to help reduce or prevent the impact of scaling or fouling of the UV lamp sleeve. This is a low pressure UV lamp. So that's one thing that was unique to that case study. But I'll talk about that one in more detail. This was in KwaZulu-Natal, and it was with Lawrence Berkeley National Labs. And then the next one, this was, I say nationwide Rwanda because it was installed in several primary schools nationwide through, this was submitted by Tani Telgenhoff from NADAP, which is, I think it's a company in the Netherlands. And so they were treating drinking water for several primary schools throughout Rwanda, actually primary schools and small hospitals. But this is a solar powered system, and they used bag filtration to filter the water prior to the UV treatment. And then we have these two for Maramba and Muganero, Rwanda. And these were submitted by Evan Thomas, who's now a professor at the University of Colorado, and was familiar with the system, the one in black and white, familiar with that one from back then. I remember it being installed. This was originally an Engineers Without Borders USA project in collaboration with the Mana Energy Foundation. And this was called a bring your own water system. So community members would bring their own water, dump it into the tank, and then it ran through a series of treatment steps. I believe it was filtration, gravel and sand filtration prior to the UV system. And that was 2005 to 2007. And then the next iteration is the one in the bottom left. So this was 2007 to 2010. And a couple of unique things about this one. One is that they started to use carbon credits for financing it. So that was a unique funding strategy. And then another unique thing to point out is that they also had monitoring sensors. So they were monitoring the UV transmittance to see how is that changing over time. And they also had multiple UV lamps in parallel. So they could choose which one to use. They could choose a smaller lamp for low flow rate and good quality water, high UV transmittance, meaning more of the UVs actually reaching the target microorganisms of concern. But then they could also use a different lamp, a larger lamp if they needed to, if they had either more volume or worse water quality. So that was something unique to that system. And then in the top left, we have one from Gulu, Uganda, and this was submitted by Mitch Hansen from Aquasense Technologies, so a company that makes many LED devices that are used worldwide. I think that they're participants in a few of these case studies, but this was done in collaboration with the African STEM Initiative. And I should mention, I see that there are some questions coming up in the chat. I can't see those yet while I'm presenting, but there'll be time for question and answers at the end of the presentation. Oops. Now I'll move on to Asia. So covering the 5 different case studies that we included from there. So again, I'll start in the top right and go clockwise. So the one in the top right, this is in Laos, People's Democratic Republic. And I took this picture, actually. I got to see this system when I was living and working in Thailand at the Asian Institute of Technology. I got to visit it. And this was actually, I'll talk about this one in more detail, but for now, I'll just say this was the only one that worked focused on wastewater of all the 19 case studies that I'm mentioning. So then I'll go to the Panabalan Island one in the Philippines on the lower right. And this was submitted and worked on through the University of Tokyo. Dr. Kumi Aguma submitted this one, and she was working in collaboration with the University of San Agustin in the Philippines. And this was a community of 50 people on an island in the Philippines. They had groundwater contamination in all 9 wells. So they set up the system. And what was unique to this one is that they weren't just monitoring E. coli. So we find that a lot of the systems and a lot of the water quality monitoring, it monitors only E. coli as a water quality indicator. And here they also did DNA sequencing to figure out what are other organisms of concern. And one that did show up, that was Shigella. So that was one of the organisms of concern. And this one's been published if you're interested in learning more about it. Next one, so one of the 3 from India. So this one at the bottom is from Tamil Nadu, India. And this was submitted by Professor Kanmani from Anna University in Chennai. And here, one of the things that was unique about it is that the water source was a rainwater collection pond. So it's called Urani. And I mentioned earlier about turbidity being one of the challenges. And I believe that was a challenge in this study because of the variation in water quality, in rainwater quality. Especially when it's collected in pond form. So that was one of the things to highlight from that study. And then the next one at Karnataka State, this is in India, and this was done through our collaborators, Hadas Maman and Dana Pausti from Tel Aviv University. And here they had a flow-through UV LED system to treat water from the Krishna River. And here, the community already had access to reverse osmosis at these treatment kiosks, but the challenge is the long distances to walk to get to that water, to be able to access that treated water. And so this was set up as an alternative to walking long distances for reverse osmosis treated water. And then the top right, we have a system, the UV Waterworks that I started mentioning earlier. This is in Bhupalpur, India. And this was it was the oldest system studied. So that's actually a good segue into the next few slides. So now I'll cover 4 of these ones in detail. So just give you more information, and then I'll go into some of the common themes that we noticed, like what were the main challenges of using UV in these kinds of water treatment situations. So this one, the UV Waterworks, this was the oldest case study that we mentioned. So UV being implemented in 1994 and 1995. And this was due to a cholera outbreak that they had in the community in 1993. And I mentioned it was a collaboration with Lawrence Berkeley National Lab in Berkeley with funding from USAID. And so they did testing in the lab and then installed it into the community. And initially they had a system that was 60 liters per minute and found that was not necessary. So they scaled it down to 15 liters per minute. This was serving 500 to 1,500 people. And you can see the UV Waterworks system, it's encased by this concrete box. Contaminated well water was treated through that system. And let's see, trying to remember the total costs of this one. Actually don't have that, but they estimated that over its lifetime, it would cost about 2 cents per ton of treated water. And it was designed for a target UV dose of 120 millijoules per centimeter squared. If you're in the industry, that's about 3 times the normal dose of 40 that we tried to apply for drinking water treatment. And it had a more than 6 log reduction of E. coli, but that's how much that they were detecting, and they reached the limit of detection. But then one of the things that's unique to this one is that it was operated by the 12-volt car battery. Next one that I wanted to talk about. So this was, I would say, out of all the case studies, this was the largest study population. So 600 rural households in rural Mexico. And basically there were, they did randomized control trials. And here we had a community where people could practice boiling or point of use chlorination, or several communities, I should say, but they weren't. Only about 5% of the population surveyed was practicing boiling or point of use collaboration or chlorination. But one of the incentives for using UV in this area is that electricity is widely available. And of course, you need electricity to power UV lamps. So that was one of the incentives to use UV. So they started with this Mesita Azul, which is the picture on the left, and had this in households, about 400 households from 2006 to 2014. And they were measuring, again, water through a low pressure UV lamp and measuring E. coli and how much did that decrease when people were using this system. And basically they did see an E. coli decrease from 60% down to 20%. They also saw an increased use in ultraviolet disinfection technologies, which is good. But one of the downsides of this one is that there were alternative disease transmission routes. So basically they were only treating the drinking water. And so there were alternative contamination through wash water, through other sources of water that people were using for bathing or washing clothes. So that led to the next iteration, which was the safe water system. So here in the bottom right, and these were 250-liter storage tanks and treating all of the water that was being used by the community. And here, so they did see a decrease in E. coli from 80% down to 20%. And they also saw 16% of households were still using non-treated water. So there were still, again, alternative disease transmission pathways that way. And there were two different types of UV systems. Some had the UV that was submersed in water. And when you have that, there can be challenges with fouling or scaling of the UV lamps with organic or inorganic contaminants kind of coating the quartz sleeves that cover the lamps. And so they also had the open channel system where the lamp was suspended above the water. I wanted to mention this study. This was the one that I saw in Lao, a PDR. So this was done. Basically, they had an activated sludge at a wastewater treatment plant, and that system failed. So then BORDA, which is a German NGO called the Bremen Overseas Research and Development Association, they were called in to install a wastewater treatment system. And they had this treatment plant with a settler, an anaerobic baffle reactor, anaerobic filter, and a planted gravel filter. That was all the pre-treatment process prior to the UV disinfection. And for UV, they had 4 low pressure UV lamps in parallel, like you see in the picture on the bottom. And so they installed this in 2011, and then 5 years later, we're having problems with it not working, and they weren't able to meet their E. coli targets. And so they asked us to come in and take a look at it and see what was going on. And there were a few things that were going on. One is that the flow rate they were using it for, that exceeded the manufacturer's recommendations. Also, the total suspended solids were too high, which we assume was due to insufficient pre-treatment. So this planted gravel filter had been in use for 5 years. There wasn't really any maintenance to regenerate what was in there or anything like that. So the total suspended solids were too high. And they also had high fouling and scaling of the quartz sleeves that were covering the lamp. And I should say this is in Lao, where there are a lot of limestone foundations. So calcium carbonate would be higher in the water source there. The lamps did have this manual wiper that you can move back and forth, and we think maybe that they weren't doing that or also weren't following a cleaning protocol. So there was irregular operation and maintenance. So even though they had been tracking the lamp installation, the lamps were only 6 months old, there was an issue with the fouling and scaling. And so they were looking at ways to treat that, to troubleshoot that. And then I wanted to highlight this one because this is part of the research that we're doing in my research group. And so, like I mentioned, this is at Dr. Paul Ankundi Nyangaresi's at his hometown in Yamoussoukro, Kenya. And there he's got, the community has like many, had issues with waterborne diseases, and even this year had deaths from amoebic dysentery. So this is a prototype of a household water treatment system with rainwater harvested from corrugated iron roofs. And it's running through the first tank, which is multiple layers of sand and charcoal filtration for removing debris, but also removing chemical contaminants and also reducing taste and odor. And then they've got that pre-treated water that's stored in the tank on the left. And that's what's run through the UV LEDs, which you see in this picture on the left. So that's a Clarin unit from Crystal IS. So that's a small UV LED system, and they treat it at the tap. So this is treating at the tap. And I mentioned earlier that one of the things that's unique about this case study is that it's gravity driven. And so we're trying to reduce costs associated with pumps. So then what are the overall challenges and considerations and limitations of using UV? I have people ask me, like, is UV ready for household water treatment? And it's not only ready, I mean, it's already being used. We saw, like, dating back to 1994, and we saw 600 households in Mexico. So it's certainly ready and it's in use. And now the challenge is figuring out, what are challenges in these systems? What are problems that come up? And then how do we mitigate those? Like any household water treatment systems, there are pros and cons. So how do we mitigate some of the challenges? And I kind of divided it up into these 6 different categories. So the first one is availability. So how available are these? Can you get parts if you need? Do you have a supply chain in place? Of course, with any system, the lamps could fail. LEDs may need to be replaced. And is that possible? And is it easy with the supply chain for a given community? Also, there's the issue of affordability. And one of the things that Paul mentioned for the last slide, the rainwater system in Kenya, is that the total system cost was about $200. And this is in a community where people are earning about $1 a day, and it's predominantly subsistence farming. So is that cost sustainable? And then there are also issues with scaling up with population growth, and how easy is that to do for UV systems? The next category, water quality, is a big one. And I mentioned in a couple of the studies where they saw turbidity spikes due to increases in turbidity from seasonal water variations through source water, like surface water, and also, predominantly surface water. And how do we deal with turbidity? So is the filtration step enough? Is there enough operation and maintenance of whatever filtration system you have in place? So that was a big one, a big consideration. Also chemical and biological fouling. This wasn't just with the wastewater project where they had fouling and scaling of UV lamps, but lamps that are submersed in the water will have that issue where there's chemical and biological fouling. So how can we anticipate that? And what's the appropriate cleaning schedule for cleaning the lamp sleeves? And then also water quality monitoring, and when does it make sense to install monitoring sensors, and then what parameters would you want to monitor for? But basically, whatever you're feeding into the UV lamp, you need to keep it within certain parameters for the UV to be effective. And the next category is a system design. So the location of the water system, and basically you need to treat the water along the whole treatment train, right? So looking at the source to tap. And this is interesting because if you put the UV device too close to the source water, then you could have recontamination up through or into the home or school or what have you. But then if you put it at the point of use, you can have other issues there. So it's really deciding like the design of the whole system, but then also the design of the UV system. And so with the UV system, we noticed some of these had poor user-focused designs. You couldn't tell if the UV lamps were still on. You couldn't tell if they had failed. And one thing that was unique about that UV waterworks system is that they had the second iteration had a window, so users could see, they could make sure that the light was still on. And then also I mentioned difficult to inspect and clean. So we have to make sure these are easy enough to inspect and clean. Typically with the low pressure lamps, that's easier to do. With the LEDs, it can be sometimes harder depending on the design of the device, sometimes harder to inspect and clean it. So how can we really simplify the whole design to make it easy? Next 3, so first, power requirements. So since it's UV light not coming from the sun, we need an energy source, and these had grid solar and battery. With the grid sources, we can see issues with intermittent electricity. And then one thing I wasn't anticipating, and neither were they in the case study, but the energy surges. So even using charge controllers sourced from elsewhere, they still had issues with these power surges that were burning out the lamps. And how do you deal with something like that? Also, in some cases, with electrical housing, if it wasn't encased or enclosed enough, there could be issues with animals chewing through some of the wires. So that was a consideration. And then with the systems that had solar power, of course, there are seasonal variations in solar and sunlight. Operation and maintenance is probably the most important one. So if you have insufficient training of your operators, then you won't be able to maintain the systems, right? If you have good training, you'll be able to deal with probably all of these issues. But some of the things that we saw were poor attendance during installation, or else maybe you had a great operator, but you'd have inconsistent use of the UV if school was not in session, for example, or if there was staff turnover, there wasn't enough knowledge transmission from one operator to another. That was an issue. And then what we see with a lot of development projects, if they're not initiated within the community and there's not enough project follow-up, or the people haven't built the capacity in the community to deal with the system and properly maintain it, that can be an issue as well. And then the last one, social trust and buy-in, making sure that you have community buy-in, making sure you have community trust. And then are there specific regulations that can either prevent or support the use of UV? And then are there sufficient business models that can help to offset the capital or maintenance costs with the systems? I just wanted to mention this again and encourage you to take a look at the International UV website and click through some of them to learn more about the systems. And with that, thank you for your time, and I'll open it up for questions.